Otherwise, let me know that I will turn off my camera.
Perfect, go ahead.
Okay, so good morning, good afternoon, good evening, everyone. My name is Giovanni Volta. I'm a PhD student at the University of Zurich, and I'm working in the Xenon and Xenon experiment. And today I'm going to show you the current status of the Xenon and TON light cells. First, let me introduce you the Xenon collaboration. The Xenon experiment is a dark matter dye detection experiment, which aims detection of dark matter in forms of WIMP through deploying a dual-phase Xenon time projection chamber. The experiment is placed at Laboratorio Nazionale Gran Sasso in Italy, and we are quite big collaboration over under 70 scientists all around the world, as you can see from the picture. The experiment started in 2006 with the first prototype, and up to now we saw 3 phases, and we are currently in the fourth one, Xenon and TON, which is taking data right now. So the Xenon experiment, Xenon and TON in particular, is not just the dual-phase time projection chamber, but it's a more complicated experiment. We actually have 3 detectors. The first one is a water tank, a huge water tank, equipped with PMTs, which act as active Cherenkov veto. At the center, close to the TPC, we have optically separated from the muon veto and neutron veto in order to improve the background reduction due to neutrons. But yes, of course, the main character of the experiment is the dual-phase time projection chamber. It is basically a cylinder of 1.5 meters high and 1.3 meter diameter, which the volume is defined by the high reflectivity PTFE panels and from two PMT arrays with in total 494 PMTs. And today we are talking about these PMTs. The PMTs using Xenon and TON, they were the same type using Xenon 1 TON, and they are broadly used in the community of Xenon experiment. They are is L11410/21. This PMT, the type 21 has been developed between the collaboration of Xenon and Amamatsu directly, where we try to minimize the radioactivity contamination for each component and maximize the response at the xenon scintillation light, as well as the performances at the xenon liquid temperature. On the right, you can see the sketch of the PMT. I think I don't have to explain you how a PMT works. Just let me point it out that in order to bias the dynamic chain for the amplification, here the voltage divided circuit has been developed, is custom made from the collaboration itself, in particular here in Zurich, and is such that the linearity is conserved up to 1 eV, so well far from the dark matter region, and the dissipation, the power dissipation to detector is very, very low, and it's not a problem for liquid xenon temperature. And here a picture of the PMT. Okay, the PMTs, we have 494 PMTs, as I said, and 341 were new, and each of them have been tested within the same environment of xenon and TON. So we perform at least 2 weeks in liquid and gas xenon. I'm not going through the PMT testing phase, since you are going to listen soon from Luisa. But just keep in mind that the results of this testing can be used to reject the bad PMTs and to choose where to allocate the good one in the TPC. Before show you the current status of the PMTs, I think it's very nice to see the cleaning and the assembly period. So as part of a background mitigation program campaign, the assembly as well as the cleaning has been performed in a clean room ISO 5, standard ISO 5. And each component has been cleaned using different procedure according to the material. For instance, the cables for the PMTs have been here. One of the steps was in cleaning ultrasonic bath con deionized water and acid soap. On the other hand, the PMTs were just we soak in the ethanol, and very pure ethanol, 90%, 0.9, and wipe it out carefully and dry it with nitrogen. and then they've been placed for using a very detailed cabling plan, such to minimize the amount of cables and to help the procedure of the assembly. Here, a picture while we were mounting, we will assemble the top PMT array, and here when it was over. Here, right. At the end, we tested all the connectivity point on the basis, as well as we perform a actual PMT test using a light type box before store the arrays in a clean environment, waiting for the TPC assembly. I don't have time, and it's not my objective today to show you the TPC assembly, but here a picture during the operation of the turn of the top PMT array before inserting under the bell during the TPC assembly, and here the TPC right before closing the inner cryostat. What about the PMT cabling? So we have a lot of PMTs for 94. For each PMT, we have 3 cables. So you can imagine the number of cables. We have roughly 16 kilometers of cables, and that correspond to 60 kilos. So a lot. We have a coax cable for the signal readout, while for the high voltage and the grounding is provided from coupled inserted wires. Here, a sketch how the cabling plan has been done. We have the TPC are 2 connectors in order to connect the TPC to the service building next to the water tank that hosts all the facility, to run the experiment, and the cables run through 2 cryogenic pipes, and they end up on a vacuum breakout chamber that helps to connect the vacuum side to the air side. Here, the captain cables are directly connected to the power supply, while the signal have been passed first through a custom-made dual-channel amplifier, and then they go to the analog to digitizer converter. Okay, of course, for the PMT, we also need a very reliable calibration system. And in Xenon and TON, which is kind of inherited from Xenon 1 TON, we perform a weekly calibration of our PMTs using a blue LED, which is coupled with the cryogenic optical fibers, which bring the light inside the TPC, all around the TPC, such to have a uniform light distribution. The data acquisition, which is triggerless and is externally triggered from the DIQ, and the acquisition window as well as the frequencies can be adjusted in order to perform different kind of analysis. Indeed, we monitor we calibrate for the single P amplification, also as a gain and after pass, which needs 2 different types. And also, let me tell you that the raw data are processed with a brand new software, Strux, in particular for Xenon Strux, and here the reference. Okay, right. So let's go through the performance then. The Xenon and TON, the PMT are on basically since the spring of 2020. So we at the very beginning we perform a quite long campaign of commissioning, and one of the objectives was reduce as much as we can the electronic noise in the TPC. Here you can see the pedestal root mean square for all the PMT channel, and as well as the projection, so basically the histogram. And as you can see, the noise is quite low, 0.23 millivolt to 0.3 millivolt for bottom and top. So even if there is a discrepancy between top and bottom, it's still quite low. And these 2 data sets comes from May 2021 and September 2021. And with these, I want to point it out that we actually also observe quite stability in the noise. On the right, instead, you can see the Fourier transform of the noise calibration run for the amplitude for each frequency as a function of the PMT channel, as well as the cumulative sum. This is a quite nice and important parameter space that helps to understand the source of the noise in order to reduce them. So yes, we are quite happy for the level of the noise. another important parameters that we are monitoring and it needs to be characterized is the single photoelectron amplification, and so the gain, as I said before. And this is computed using a model-independent method. I don't have time to go through this method, but here, if you are interested, I posted here the reference. Right. So we perform at least a weekly evaluation of the gain, not just to monitor the performances, but also to have a time-dependent gain model that is fundamental for quality of the processing of the offline processing for the science run data. The situation of the high voltage right now, so the gain has been chosen after a quite intense PMT performance optimization, where all the performances have been are maximized. We try to maximize the performance of the PMT. Here you can see a distribution of the gain in the current configuration, and that you see that is around 2 million, and it's quite uniform between top and bottom. The gray dot instead are the PMT which is currently off. While on the right, I want to emphasize after the HV optimization, when we froze the voltage setting, I want to emphasize the stability of the gain that we achieved. Through the weekly calibration PMTs, we also monitor the single photoelectron acceptance and the single PA resolution, which is fundamental for low energy sources, since they are one of the main features that to decide the self-trigger threshold. So in order to decide when acquired data and for low energy, it's very important to have a good resolution and acceptance. This is computed using a dedicated low illumination run in order to minimize the amount of events above of 2-3 above very high PE. On the top, you see the SP acceptance, while on the bottom, you see the SP resolution, which is computed using a fitting method on this time, using this low illumination run. And the shape is also used as input for the framework.
2 minutes left.
Okay. Last, let me, the last things that we monitor and we actually follow up is the after pass rate using a dedicated high illumination runs. And this is quite important. And we among all the sources that produce after pass, we are in particular interested on the residual gas concentration. Here on the right, you can see the distribution of the after pass rate for the cumulative total after pass rate. But we are mostly interested on the xenon, on the ion xenon after passes, because they are related to vacuum problems for the PMTs, which can arise, can produce quite problems also in the quality of the data. And we currently observe something like around 17 PMT that show xenon after pass rate, like here PMT 296, you can see, but just 3 of them have slight increase after pass. And just let me stress that this is quite good status compared also to the previous experiment. So I hope I convinced you that the PMTs, we are treating the PMTs quite well, and they are safe. And currently we have quite a stable condition with a uniform single PA amplification and 2 million and acceptance, that is overall above 90%. It's not finished here because we have to characterize other features and keep monitoring the PMT performances in order to optimize the data quality for the incoming science data. And with this, I finish, and thank you for that attention.
Thank you, Giovanni, for this really nice talk. So I think we have time for 1 or 2 short questions. Leah?
Hi, so I had a number of questions. I'll just choose one randomly. You said that a few PMTs are not working. So this happened after cooling down?
No. So few PMTs, actually, the majority of them, we were not able to turn it on at the very beginning. And this is probably due to problems during the assembly that we didn't spot at the beginning. just let me, this can be a controversial discussion also, but let me just point it out that the majority are at the bottom of PMT, so these at the bottom array, so these are less problematic compared to the top. And so yes, while few PMTs instead, they are not off, but we decide to remove from the analysis because we were not able to optimize enough the performances. And so in order to don't ruin the quality of the data, we choose to remove it.
These are the same PMTs which are not part of the 90% acceptance?
Yes, they are not part, no.
Okay, thank you.
You're welcome.
Okay, thank you. So I think we should go on to the next talk. Also, no one else raised their hand. Thank you again, Giovanni. And now we continue with Luisa, so you can share your screen and go ahead.
Hello, hope you can hear me.
Yes, very well.
And you should see my screen right about now.
Yes.
Very nice. 1 second. All right. I hope you can see the presentation and hear me.
Yes, perfect. You
Very
can go
well.
ahead.
Oh, all right. Okay, hi, my name is Luisa. I want to talk to you today about the improved quality test that we did for the R11410 photomultiplier tubes. This PMT is produced by Hamamatsu and is still the photosensor of choice for many of the large liquid xenon TPCs. For example, the Xenon Anton experiment, the LZ experiment, and Panda X are all using currently this PMT type. Next and Red also have used them in the past. And you've already heard from Giovanni about many of the advantages of the PMT. But there are also some known issues, which are mainly the effect of light emission and also an imperfect leak tightness of this PMT. So in order to detect these issues early, preferably before one installs large numbers of faulty PMTs inside a large detector, we developed some new and also improved old PMT testing strategies in order to detect these issues early. So in total, we tested 368 new PMTs for the Xenon Anton detector, which was a testing campaign over several years, the results of which are published in this paper here, and I will also show them to you in the next minutes. Right, so the testing campaign has been performed as a joint effort of 3 testing institutions, namely the Stockholm University, the University of Zurich, and the Max Planck Institute for Nuclear Physics in Heidelberg. In total, we have 4 testing setups, one where we can perform general characterization measurements at room temperature in a low noise Faraday cage environment, seen on the left here. And we also have in total 3 cryogenic testing setups where we can test the PMTs at cryogenic temperatures at -100 degrees. One where we can test the PMTs in a gaseous argon atmosphere for 1 day. And more importantly, we have these 2 setups here where we can hold the PMTs immersed in liquid xenon or gaseous xenon for 2 weeks in a row. We actually made sure that we tested all PMTs for at least 2 weeks in xenon. Now let me start with some general characteristics. The average quantum efficiency that we have of the set of new PMTs is 34%. This is actually measured by Hamamatsu, not by us. And if you compare this to the values from our previous testing campaign, which was for the Xenon Anton detector, you can see that this is basically has stayed identical. However, the gain has significantly improved since the previous testing campaign. So the new PMTs have an average gain of 8.4 million at 1.5 kilowatt bias voltage, which is, as I said, much larger than for the older PMTs. In addition, the PMTs show a very good single photoelectron resolution of about 25% at a gain of 5 million. And additionally, they have a very nice peak to value ratio of about 4.3 at 5 million gain. But now let me come to the more important part, which is the issues. First one being the light emission. The most common form of light emission is called microlight emission, which is the continuous emission of single photons from the interior of the tubes. This is an effect that is actually present in all PMTs at a few hertz level. Its intensity is correlated with the bias voltage of the PMT, which might point to field emissions as a possible origin of these photons, but the actual cause is not known, at least not to us. Maybe Hamamatsu knows, but we don't. Now, in order to make this effect of light emission less severe, Hamamatsu implemented some countermeasures by basically adding materials to the inside of the PMT that is supposed to block the optical path of the photons out of the PMTs. Now, how do we measure this light emission in our setups? Here we can use the fact that the PMTs are distributed in these two arrays, which always have two PMTs directly opposite each other, window to window, only a few centimeter distance. And then we can measure the light emission of a tested PMT by scanning over its high voltage. And we keep the voltage of the opposite PMT constant and monitor its count rate increase. And this count rate increase we can then attribute to the light emission of the tested PMT. And in this figure here, you can see an example of a normal PMT, which has like the normal level of light emission of like tens of hertz at these higher voltages. But on the right, you can see one example of one of those very bad PMTs with strong light emission, where the rate in the opposite PMT goes up to several kilohertz. So in total in our tests, we found 5 PMTs with the strong version of light emission, which is quite a low number. And in addition, even for all the other PMTs that were good, since they have a higher gain now, means we can operate them at lower voltages where the effect is also less severe. So we also have basically an improvement in this regard here. Another type of light emission is what we call intermittent light emission. This was actually first observed in the PMTs installed in the Xenon 1-ton detector. It is a very similar effect to the micro light emission, but it is actually more intense, and most importantly, it is irregularly turning on and off, seemingly randomly. Sometimes it's on for only a few minutes, sometimes also for hours or days, which is why we call it intermittent. And while it is seemingly randomly, we have noticed that it can sometimes be triggered by a high signal rate in a detector. So in order to possibly trigger PMTs that have this issue, we added a so-called high illumination stress test to our testing campaign, where we illuminate the PMTs over several hours at a very high intensity with our LEDs. You can see an example measurement here, and the period that is shaded in this bright gray, the high illumination was on. You can see after several hours, this blue PMT suddenly starts emitting a lot of light, which is also seen by the opposite PMT here, which also shows then an increased count rate. This light emission actually extends to after the period of the high illumination. We did a quick cross-check here that you can see in this inset, where when we turned off the light emitting PMT, you can see that the count rate of the opposite PMT, the good PMT, drops down immediately as well, which sort of proves to us that this really is a light emission by this blue PMT. In total, we identified 6 PMTs with this intermittent light emission, which is actually the same order of magnitude than with the normal test. And it brings our total number of PMTs with light emission to 11, which is 3% of the total number of tested PMTs, which is comparing it to the testing results of the previous testing campaign, for example, 1-ton, is really a huge improvement. And this shows that the countermeasures that Hamamatsu implemented have proven to be very effective. Now, the second problem that I want to talk about is the vacuum degradation problem, which we monitor via ion afterpulses. These are created when residual gases inside a PMT are ionized by photoelectrons. These ions can then be accelerated backwards towards the photocathode, where on impact they produce delayed pulses, which are the afterpulses. And the delay times of these afterpulses are specific to the mass-to-charge ratio of the ion that created it, which allows us to make these nice afterpulse spectra here, where we can identify these lines corresponding to specific ions. And we see, for example, that all PMTs have some amount of helium, which just diffuses in from the air. It's just unavoidable to have this. A good fraction of our PMTs show some contamination from argon, and which is already there from the very beginning, probably coming from the production process. But actually, we are mostly interested in this position here where we expect the xenon to show up in case that the PMT is leaky. So as I said before, we have all PMTs immersed in liquid or gaseous xenon for at least 2 weeks, during which time we regularly take these after-pulse measurements, and then we can check for vacuum degradation. So we observe 2 types of vacuum degradation. First one is, as I just explained, an increase of the argon rate when we test in argon, or an appearance of a xenon contamination when we test in xenon, which clearly indicates a microscopic leak. The second type that we see has a really high overall after-pulse rate with many, many lines that we can is consistent with a nitrogen contamination. This can either be from an external air leak or from internal outgassing processes. Hamamatsu actually says it's probably the second one. So in total, we find 15 PMTs with vacuum degradation, which is 4.1% of all of our tested PMTs. And again, this is a much better number than in the previous testing campaign for xenon 1 ton. In this campaign for xenon 1 ton, we were not able to test all PMTs in xenon, actually only a small fraction. So the amount of the fraction of PMTs that develop xenon leaks in xenon 1 ton is actually even larger than this number. So really the improvement here is also really, really large. During our tests, we also found an interesting effect where we observed that PMTs with high after-pulse rates can induce fake after-pulse lines in the opposite PMT. This you can see in the figure here. We have in green, we see the after-pulse spectrum again of a PMT which has a high after-pulse rate due to a nitrogen contamination. And the PMT, which is opposite, is shown here with the pink line. You can see these after-pulses that are these peaks here that are correlated with the peaks in the opposite PMT. And when this opposite PMT, the green one, is turned off, you can see that these pulses disappear. So actually this is actually a good PMT and not one of those bad ones. So from this, we concluded that somehow single photons must be emitted from a PMT in coincidence with an afterpulse. We have 2 hypotheses what could cause this. Both are basically excitation processes. It could be either during the interaction of a backshifted ion with the photocathode, which is explained as close time coincidence here. But it could also happen during the ionization process itself. That would mean that we only see this effect from secondary afterpulses, since from primary afterpulses this would happen at the exact same time as the LED pulse, so we would never see it in our setup. And this would then also explain why we only see this effect for PMTs that have very high afterpulse rates. Another interesting thing is that we found a correlation between the amount of argon that the PMTs contain initially and their probability to develop leaks later on. And this effect was actually first observed in the xenon 1 ton PMTs, but we also find this correlation here in our testing results. So 60% of our PMTs actually contain some residual argon already from the beginning. So as I said, likely it comes directly from the production process. And in this plot here, we have on the y-axis, we see the argon afterpulse rate, which is expected to be more or less proportional to the amount of argon that the PMT contains. And you can see that the higher this amount is, the more likely the PMTs are to develop leaks. So almost all of our leaky PMTs in the tests are in this region up here.
1.5 minutes left.
Thanks. So we can use this correlation when we want to decide if and where to put a PMT in the detector, since the very bad ones we would not install at all. And for the PMTs that show some argon, we can, for example, decide to put them not in critical positions in the TPC. All right, this brings me already to my summary. So we performed an extensive testing campaign of a large amount of PMTs, 368 in total. We used new and upgraded facilities for this, allowing us to actually test all PMTs in liquid and gaseous xenon for several weeks. We developed new tests targeted at this intermittent light emission effect. And to summarize the results, our PMTs have a higher gain, have less light emission, show a smaller leak probability, despite our much more rigorous testing campaign. So overall, the quality and leak tightness of the PMTs is significantly improved. And we expect and have already seen, as Giovanni has just shown us, an improved PMT performance in Xenon Anton. Yeah, thank you very much for listening.
Thanks, Luisa. Yeah. I have already one question. Leo, go ahead again.
Thank you. So I understand that these tests help you disqualify or decide on where to place PMTs which are borderline okay. But do you also apply in your ongoing analysis when you're doing data taking, do you apply PMT specific corrections? Let's say that you have a PMT that has still a high after pulse rate. Do you take this into account in the analysis? Do you expect this PMT, if this PMT has some signal, do you suspect that this is an after pulse or this is done once you install the detector?
As far as I know, currently we do not specifically correct for this, but after pulses are included in our waveform simulator. So basically, if there's any bias in S1 or S2 sizes that are caused by after pulses, this would be accounted for by matching our data to this full chain simulation that includes the waveform simulator. And I think there are some studies that are looking into how we could possibly even remove after pulses from data. But yeah, this is a very early work. Okay, thanks. I don't see any other questions, so I think we should go on. Thanks again, Luisa. So Valerio, are you ready to share your screens?
Yeah, hi, Jorn. Yeah, I start to share my screen.
So we see the agenda. Yeah, now we see your
can you
talk,
see? Okay.
But we see the two bars of Zoom. So maybe you can make the picture smaller of the video also of the other people. Get rid of that. Yeah, I guess that's better. Okay, go ahead.
Okay, so yeah, thanks, Jorn. So I'm Valerio D'Andrea, and I will talk about this new photosensor that is called Abalone. So that is a work that we are doing inside the Darwin dark matter future experiment. So I would say something about the motivation to build a new kind of a photosensor, and in particular to replace PMTs and silicon PM. Yeah, we know that most used photosensor are PMTs. That is a well-established technique, but with some disadvantage, like for example, the large number of handmade components, and this means also an intensive assembly methods. And also we know that the silicon PM have a typical area that is small, quite small, of order of a few millimeters. That means that for large area application, using silicon PM is very expensive. So the aim of the Abalone is to be a cost-effective and robust alternative to this kind of photosensor, in particular for application in large physics experiment, and also other applications like medical imaging. So I will say something about the construction of the Abalone that you can see here in these two pictures that are showing the top view and the bottom view of an Abalone. So the Abalone consists on three main components that are the dome, the base plate, and the windowlet. These three components are bonded together. In particular, the dome is bonded with the base, and is the where the high voltage is passing. Then we have a contact between the base plate and the windowlet that is the where the ground potential is placed. We have the windowlet, as I said, where we have a scintillator material, and for this application that you can see here, we use the LIDINE scintillator, and then we have a photocathode that is placed in the inside surface of the dome. As I said, we need high voltage for the Abalone for the working, and of the order of 25 kilovolts. To read the scintillation from the windowlet, also we need a Geiger mode avalanche photodiode, usually a silicon PM to detect the photons produced by the window LED. The crucial part of the construction of the abalone is that it's made only with the glass components. That means that we have no metals, ceramics, or fit-through. And this is the main difference compared to the PMTs. I will say something about the working principle. Here you can see a schematic view of the abalone. So an abalone that is interacting with the photocathode produce photoelectrons that are accelerated by the field in order to reach the center of the base where the scintillator is placed. At scintillator, we have the production of secondary photons with this formula. So the number of photons is proportional to the energy of the electrons and to the light yield of scintillator. For our case, I said we use LISO that has a light yield of 26 photons per keV. These secondary photons are read by an avalanche photodiode that for our application is a silicon PM. And here I'm reporting some number just as an example. 25 keV photoelectrons produce something like 650 photons that and 100 of those are detected by the silicon PM. This means that if the silicon PM has a gain of 6 times 10 to 6, we can have a total gain of the system abalone plus the silicon PM of the order of 10 to 8. Here I'm showing some of the main performance of the abalone. I'm reporting also two references here that you can show if you are interested. The abalone is resistant to shock or compression and is also immune to accidental exposure of light. It's made with component with an exceptional radio purity, and as I said, it has an intrinsic gain of the order of 10 to 8. Also showed a low after pulse rate and an optimal timing resolution of the order of below the nanosecond. So now with our group, we are currently working in the characterization of the abalone. And as I said, this is an R&D activity that is inserted in the activity for the future Darwin experiment. So we worked on a simulation of the abalone. So we try to reproduce the electrical field inside the abalone. Here you can see a picture of the potential inside the abalone. In blue, there is the high potential part that is basically our photocathode, and then in red you can see the ground potential that is at the scintillator place here at the center of the base. And then also you can see in the other picture example of trajectory of the particles of the photoelectron inside the abalone. Using Gent4, we reconstructed the trajectory as I showed, and we classified the photoelectron trajectories in 4 classes: the straight electrons, that are the electrons that directly reach the scintillator. Then we have the so-called returning, that are the electrons that release the energy in more than one interaction. And then we have these that are the non-returning. So this means that they release only part of the energy inside the scintillator. And then we, of course, have few undetected photoelectrons. Here, what we did in our analysis is the evolution of these 4 classes as function of the abalone voltage. And as we can see, this is the most important part is that the undetected photoelectrons are decreasing with the increase of voltage. And this is also explaining why we need this high voltage for the abalone. In red, you can see the percentage of the non-returning electrons, and how our work in simulation is try to reduce this effect, and in particular try with also other scintillator material. Also, I reported here a typical spectrum that we have in simulation, where we can see the peak due to the strayed electrons, and we can see this asymmetric peak due to the non-returning electrodes that, as I said, are the electrodes that are not releasing all the energy in the scintillator. Also, we have a setup here at Laboratori Nazionali del Gran Sasso. We have an abalone that we are testing in this black box with this holder. The abalone, we connect the abalone a silicon PM provided by the Fondazione Bruno Kessler that is connected that is read by an amplifier. Also, we use the abalone injecting light with a blue LED that is supported by this tractor that you can see in this picture. We have some preliminary results of the characterization. So currently we are ramping up the abalone with the continuous monitoring of the dark count rate and taking data with LED as I showed in the previous slide. This is a typical spectrum we have. In this case, with the abalone at 18 kilovolts, the spectrum shows two peaks. That one is connected to the single photo. One is the single photoelectron peak of the abalone, and then this low energy peak is due to the CPM, so the read of the light directly by the CPM. Between these two peaks, we have this region here that I'm fitting with this violet function that is due to the non-returning electron. Also, I'm reporting another plot that is showing the evolution of the spectra as function of the abalone voltage. And what we can see is that, as expected, the single photoelectron peak is increasing with voltage, while the silicon PM is at the same energy. So here in this plot, I'm reporting the gain of the abalone as function of the abalone voltage, and as you can see, is increasing linearly as with voltage, and is reaching a value of 58 at voltage of 20 kilovolts. This means that we have a total gain of the system abalone plus silicon PM of 2 × 10⁸, and this is also what is expected from previous work. Also, in this plot here in the right, I'm reporting the fraction of the straight plus returning electrons in green that is increasing up to 70% at 20 kilovolts. And in red, I'm reporting the non-returning percentage that is at a value that is close to 30%. As you can see, comparing these results with the results that we get in simulation, the two plots are not completely in agreement, and we are working and trying to understand why this is happening, and also we are working on the improvement of our model of the observed spectrum. Okay, and the summary of my talk. So, as I said, the abalone photosensor is an interesting solution for application in a large area future experiment that aim to replace photomultipliers. At the moment, this photosensor is proposed for the Darwin project, that is a future dark matter project based on a liquid xenon TPC. Recently, we started the abalone characterization here in our setup at Gran Sasso at room temperature, and we hope to have soon new results. Also, as I showed, we are working in simulation analysis. The aim of this work is the improvement of the performance of the abalone, and in particular, the reduction of this effect of the non-returning photoelectrons. For example, try with different scintillator material. Also, we have a test facility in Stockholm that currently we are updating And here we want to test the abalone in cold conditions, so both using cold xenon gas and liquid xenon. So our hope is to hear soon about the abalone. Thanks for the attention.
Thanks a lot, Valerio. Really interesting. So we have time for a question or two. So if no one has some, so you were talking about that your experimental results were not yet completely identical to the simulations. So do you think the simulations are not yet perfectly modeled, or do you think you have maybe some uncertainties in the measurements? What's your guess?
Yeah, probably we think that we have to try to better model the experimental results, since we have yeah, as I showed, we have 3 populations in our spectra, and we aim to improve our yeah, basically our model to identify these 3 different regions. So we think that we have to improve our experimental results, let's say.
I see. Yeah. Okay. Well, looking forward to hear further from you. So I think then we can go to the next talk. Thanks again, Valerio. Yeah. So the next talk is Massa. I don't know how to pronounce it correctly. Maybe you can let me know.
Hello, can you hear me well?
Yes, we can hear you very
fantastic.
well. Yeah, and we can see your.
All right.
That's perfect. Go ahead.
So thank you. I'll talk about transparent gem type detectors with wavelength shifting capability for noble element TPCs. This is a work which has been recently published. For your convenience, I linked the paper to the Indico, and this is a collaboration between several groups. So here's the full offer list. And I'll essentially walk you through our results in this talk. So I will not spend too much time on the motivation for technologies useful for scale-up of gaseous or dual-phase TPCs. We all know experiments are growing in size. It's for dark matter searches, neutrino experiments, other applications. For TPC specifically, there are a few challenges which are important. Stability, uniformity of response for dual-phase TPCs is the leveling of the liquid surface. Overall efficiency, also especially because of the VUV light, which we have to deal with, either convert or directly detect. So this is one of the ideas which help this challenge. And it's one of those which integrate light and charge collection into one system. So it's gonna have simplified optical readout and then low noise. Now, this is really building on previous concepts, and just to quickly show the inspirations, thick gems have been known for a long time. These are thicker, meaning several millimeters thick, gaseous electron multipliers. Essentially, you have an insulator plate with an array of holes. You apply the electric field on both sides. Drifted electrons accelerate in a high electric field gradient in the holes and generate either electroluminescence or cascades of secondary electrons. So that idea has been around for a while. More recently, fat gems were introduced. So these are slightly thicker, and the electrode is made of metal mesh and partly transparent to visible light. Higher thickness allows to read out electroluminescence and optimize for energy resolution. Also, in this conference, you have and will hear more about PEN, not only as wavelength shifter, but also as a scintillator, particularly for legend production of scintillating wavelength shifting plates made of PEN was developed. There will be a talk later today. Finally, for a while now, P.PSS-based transparent electrodes have been out there on the market, used, for instance, in Next White. So collecting all these ideas together and using them creatively, we came up with a concept of that type. So essentially take a fake gem-like detector, but make it both transparent to visible light and wavelength shifting for vacuum ultraviolet. This is achieved with transparent electrodes, with wavelength shifting base plate, for instance, made of PEM. And that's essentially it. You can then locate an array of photosensors in front of such a structure. And the way it works is for S1, you essentially have more or less standard wavelength shifting and then propagation of visible light. So as long as this is nicely transparent, there are not too much losses, light collection can be extremely high. For S2 though, we have something interesting happening. So VUV light is generated here in the holes from electroluminescence. And because the walls of the hole, the tile itself, is wavelength shifting, they are converted to visible light on the spot. And this has some advantages. So I'll get to that. So that's the concept. Now, one of the biggest challenges is the transparent electrode. For this to work, it has to be transparent to VUV. We've experimented with P.PSS conductive polymer. This is a compound which you can commercially buy. It's available in solutions. There are multiple methods to make coatings out of it. Painting, airbrushing. We used airbrushing because we did want to optimize for as thin coating as possible to achieve optimal transparency. And by that, I mean something of the order of 10 nanometers. So this is extremely thin. At such thicknesses, this is essentially transparent, about 99% transmission to visible light, pretty much invisible by naked eye. And this can be deposited manually. We use sort of arts and crafts airbrush. There are also obviously industrial spray machines that can cover really large surfaces with that. In any way, this is a very simple and fast procedure. So after making these conductive coatings, you drill holes in your base plate and you have a ready structure. This slide, well, this plot was flashed yesterday in one of the talks. I'll say some more about that. So this is our measurement of essentially conductive electrode transparency to VUV light. It is a combination of two measurements. So the green band is measured with a spectrophotometer equipped with an integrating sphere. And here we basically took a PN tile coated with PEDOT. You put it in the integrating sphere and illuminate it with UV light. But the specularly reflected component of that light exit the sphere is not registered. There is very little diffuse reflection because it's a smooth substrate. So what you end up registering is really wavelength shifting. The more wavelength shifting you have, the more signal you see. Making a relative measurement with and without P.dot coating, we can see how much light we lose. So what's the absorption in the coating? And with this instrument, one can get to about 190 nanometers. So below, we use the vacuum monochromator at Munich, which we could use to add some additional data points, in particular the one at the liquid argon emission wavelength and liquid xenon emission wavelength. And the bottom line, for liquid argon, we only lose about 25% of VUV light, which is not bad. And this was really our first shot. This can be further optimized. The next question is, well, the conductivity. You want these electrodes to be conductive. P.dot, especially at these extreme thicknesses, is not really well explored. So at Santiago de Compostela, we used a cryogenic setup where a film sample with glued electrodes was brought to a cryogenic temperature. This surface resistivity profile as a function of temperature was measured. And we see that starting from about tens of mega ohms at room temperature, after the cool down one gets to something an order of magnitude higher. This is actually good for spark protection, and this type of devices you do aim at resistivities of that order. So it works just fine. Now, having this transmission in place, we can try to simulate light collection in such structures. And I'll ask you to ignore pretty much most of that table. We are focusing here on some idealized cases where we assume no absorption in the tile and perfect wavelength shifting efficiency. And I'm going to show you three configurations. One is without the tile. This is something like a wire mesh TPC-like detector. You're accelerating gas, you detect above it. And two example configurations with a tile. One has a 3M ESR reflector bonded at the bottom, one doesn't. So these are wavelength shifting tiles with transparent electrodes. So imagine we start with VUV emission in the hole. Those rays expand in all directions. Conceptually, well, they reach the material, they are wavelength shifted. Light propagates isotropically after wavelength shifting. And one thing you can immediately notice is in a wire mesh TPC-like configuration, because of isotropic re-emission, you lose half light immediately. In this configuration, without the reflector, there is some gain because half of the light converted in the tile, this is a significant solid angle, makes it to the photosensor. If you put a reflector at the bottom, this is even further increased. Obviously, this is just a cartoon, but we have simulated all that with GEANT and defined a figure of merit which captures that gain factor. And you can gain between a factor of 2 and 3 compared to a wire mesh TPC-like configuration. In terms of the hit pattern, which is important for position reconstruction, there is no significant loss. I'll not get in too much detail on this figure, but well, this is S1, this is S2. S2 is more interesting. We have a VUV component, so stuff coming directly from the hole, and the wavelength shifted component. So you see it propagates a little bit through the tile. But the increase in resolution and the point spread fraction is not very dramatic. We are at the level of about 10 millimeters width. This is compatible with a very good position resolution reconstruction, also based on some recent work from Next. So significant enhancement in light yield, no major loss in point spread function, which is a good indication for position reconstruction. Here are some structures we developed, and we made a proof of principle test at Santiago de Compostela, testing the high voltage stability first. So these could survive up to 6 kilovolts in air. We collected data at 4 kilovolts at 2 bar xenon, achieving decent energy resolution. This is calibrated with 5.6 kV X-rays from an iron source. Finally, there was also a run with
2 minutes left, just sorry.
Thank
Go
you.
ahead.
This is a schematic of that setup, so just with a PMT. And finally, there was also a run with argon. And we did see nice signals from argon at 4 bar, I believe. So this is the indication of wavelength shifting occurring in that system. And the PMT is blind to argon scintillation, and in previous runs with argon without wavelength shifting tiles, it saw no signal. So this is the first demonstration. So we intend to continue this effort. I guess to highlight this again, that the main feature of these structures is enhanced S2 collection by a significant factor, while S1 can still remain very high. Easy and scalable production, intrinsic radio purity, initial stability tests were successful, which is non-trivial, especially for PDOT coatings. We will characterize and optimize these devices further. There's some room for improvements. In particular, PDOT spark immunity is something that we worry about. Also, the wavelength shifting efficiency of the tile could be improved. The PN tiles have only about 10% efficiency. So there are many ways to improve it. Finally, there are other possible operation modes for structures like that, which are interesting and worth testing. Could be LHM-like, maybe even floating on liquid argon surface. I think there's a talk about LHMs coming later, so well, I'll leave you with that. Thank you.
Thanks a lot. So time for one question. Yeah, we have one again. Yeah.
Sorry for barging. So can you go back to the slide about energy resolution with ion 55?
Yeah.
So can you estimate what would be the electroluminescence? So imagine that you replace the electrode now with the just two meshes and use ion 55. What is the expected energy resolution then? And if it is worse for the FedGem, can you estimate what are the mechanisms that affect it and whether this can be improved still?
Right. So this level of energy resolution was achieved with FabGems before, just with let me go back. In this configuration, so that paper from 2020 without wavelength shifting, and I think this is a very good result overall. With our current wavelength shifting structures, we are basically showing that it didn't get worse with PDOT electrodes and all these additional features which were added. But I can refer you to this paper, which shows energy resolution versus energy, and we expect it would look identical for these wavelength shifting structures.
Okay, thank you. I don't see any further questions, so we can go on. Thanks again.
Thank you.
So the next talk will be Arindan.
Yes, do you hear me?
Yes, so we can hear you well.
Let me share my screen. Do you see my screen?
Yes, we can see it. Okay, please go ahead.
Okay, can I start?
Yes.
Okay. Hello, everyone. I'm Arindam from the Ben Gurion University, working jointly at the Weizmann Institute. And I will present today our results of the bubble-free liquid hole multiplier, the LHM, which is a new concept for primary and secondary scintillation detection in noble liquid detectors. So before I introduce the new concept of the bubble-free LHM, let's first recap the bubble-assisted liquid hole multiplier, or the standard LHM. So basically, the LHM, as shown in the schematic here, consists of a perforated hole electrode, the gem or the thick gem, coated with a cesium iodide photocathode, which is immersed completely in the liquid, and a bubble of noble gas vapor is trapped underneath. Now, an event in the noble liquid generates S1 primary scintillation photons and ionization electrons, and the S1 photons extract photoelectrons from the cesium iodide photocathode. The photoelectrons and the ionization electrons are focused into the holes where they produce electroluminescence signals S1 prime and S2 as shown here. Shown here is a recorded waveform of an alpha event. And as you can see, we have the S1, S1 prime, and the S2 signals, which are detected and localized by an array of silicon PMs located below. Now, as concerns were raised about the liquid gas interface in large area TPCs, the reason why the LHM was conceptualized was, in this case, we would have a stable interface below the thick gem, and we have very good energy resolution, S2 energy resolution, and position resolution with the LHM. This was extensively studied at the Weizmann Institute, and these are a list of publications. Cesium iodide photocathodes have very high quantum efficiency in liquid xenon, as was observed here and presented in a previous LIDINE conference by my colleague. And we show here quantum efficiencies of the order of 30%, which are similar to the numbers measured by Aprile et al. In '94. And the quantum efficiency in liquid xenon is higher than what we expect in vacuum. Since we have high quantum efficiencies, the next step is to estimate and understand what the photon detection efficiency values would be. So we have extensively studied several hole geometries, the thick gem, the gem, and the single conical gem. And in all cases, the expected PDE values, as shown here as a function of the voltage applied across the thick gem, are very high. And we can expect maximal PDE values of 20% or higher, around 20% for the thick gem, and even higher for the single conical and the normal gem. However, in the actual experiment in the LHM, the measured PDE values were always less than 5%, which brings us to the question that why did we have such low PDE? Shown here is a COMSOL simulation of the electrode placed in the liquid with the bubble trapped underneath. And as you can see, this is the liquid gas interface shown here. Now, the hypothesis that we have is the low PDE is a result of the low transfer efficiency across this interface. And we believe that the electrons are possibly lost to the electrode wall while they glide on the liquid gas surface interface. There are ongoing efforts to understand the bubble physics and the interface properties. So let me now introduce the new LHM concept, or the bubble-free DTS LHM, as we call it. So the guiding principle here is we want to take the interface away from the hole to avoid photoelectron loss, and so that we can regain the high PDE. So how it works is we have a thick gem or any other hole electrode immersed in the liquid, and there is a layer of cesium iodide photocathode evaporated on it, which effectively gives us high PDE. Once we manage to focus the electrons in the holes, the electrons and the photoelectrons, and then transfer them successfully to the gas phase, there is an avalanche and electroluminescence created in the G thick gem holes, or the gas thick gem holes. We need, however, very strong extraction fields between the two electrodes in order to avoid the loss of electrons either to the top of the thick gem or to the interface, and eventually to detect the signals and localize the events with a silicon PM array. So what are the advantages of this particular new concept? Here, as you can see, the S2 light is produced predominantly in the G thick gem holes, which means the precise location of the interface and its stability are not critical. Also, we expect to get high PDE values in liquid xenon at 175 nanometers. And as you can see, a single S1 photon is supposed to create a multi-photon EL plus avalanche light signal, which are impossible for dark counts to fake. We should be able to use silicon PMs, and this detector should have high position resolution and fast EL signals. So where do we currently stand? So this thing that we want to do right now is to first extract electrons from this cesium iodide and transfer them successfully in the liquid phase. So the idea is to focus the ionization electrons and the photoelectrons through the thick gem holes and then collect them on a top mesh and prevent them from being lost on the thick gem top. In a future scenario, the idea would be to work in the dual phase without the mesh and transfer the electrons to the gas phase where they will be detected by the gas thick gem. We also plan to study not just the thick gem electrode as we are currently working on, but also with other perforated hole electrodes like the gem or the single conical gem, where the estimated PDE values are higher. We would measure eventually the photon detection efficiencies and also the energy resolution of the system. So let me just summarize some of the preliminary results that we have obtained in the liquid phase. As you can see here, this is to show the photoelectron extraction. And as you can see, we have, for this particular test, we have the liquid thick gem and a quartz window coated with cesium iodide placed below with a top mesh above. Now the idea is to shine light on the UV and create photoelectrons, and then as a function of the drift field, study the UV induced photocurrent from the window. As you can see here, the current as a function of the drift field clearly shows that the quantum efficiency in liquid is much higher than in vacuum, which reaffirms previous observations by the Aprile group. And the higher QV in liquid xenon is attributed to the fact that there's a change in the work function of the photocathode when it's immersed in the liquid xenon. So as you can see, since we managed to extract photoelectrons quite well, the next step, of course, would be to try to transfer these electrons from the cesium iodide coat, cesium iodide coated thick gem to the top mesh. Now, as you can see, these are basically S1-like photoelectrons that are created from the thick gem with the cesium iodide coated electrode coated below. Now we operate our thick gem at very high voltages of the order of 2 kilovolts so as to work at potentially high PDEs. Now under these conditions, we have a potential concern that due to the electric field would be such that there is a possibility of losing some of the electrons on the thick gem top, and we would fail to transfer them to the top mesh. So when we tried to do the measurements on the thick gem mesh, as you can see here, mesh current as a function of the transfer electric field clearly shows that we have nearly 100% collection of S1 induced photoelectrons to the top mesh. So since we managed to do this with the S1 photoelectrons, the idea now was to, let's say, mimic S2-like ionization electrons in the form of photoelectrons created from a cesium iodide photocathode placed below the thick gem, and then to try the same to transfer the electrons to the top mesh and focus them through the thick gem holes and transfer them to the top mesh. The operation conditions were the same. We operated at 2 kilovolts, high PDE, and the concern here is we want to understand if we can do the same for S2-like ionization electrons as we did for S1 photoelectrons, so where we had 100% collection. So shown here is the result of mesh current as a function of the transfer field for S2-like ionization electrons. And as you can see again, we have nearly full collection. So there's no loss, and we focus all of the S2-like electrons to the top mesh. So it might be possible to use the DTS LHM as a potential candidate for a future TPC. So if we compare this to a conventional TPC, the L-thick gem would replace the gate. The G-thick gem would replace the anode wires, and the cathode and the PMT plane would be replaced by a cathode reflector. So as I've already mentioned, we expect to have the electroluminescence here in a very well-defined location inside the thick gem, inside the gas thick gem holes, which means we are not worried about the position and the fluctuations of the liquid-gas interface. We should have potentially high PDE because there should not be any losses. And as we already showed, we have full collection in the liquid. So it's a matter now to transfer them to the gas phase. A single S1 photon creates a large electroluminescence signal, which means dark counts should not be an issue. We should be able to lower the energy thresholds. and possibly use silicon PMs or CMOS SPAD photosensors, which will be discussed in a later talk by Michael Keller. Since we don't have any grids or meshes in the sensitive volume and a reflective photocathode, we should be able to get an improved S1 light yield. And because in principle, there are no PMTs here, we have better radio purity and no wasted liquid xenon in the buffer region. So there's still a long way to go and a lot of R&D to be done, but it's a possibility. Thank you.
Thanks for this really nice and interesting talk. So are there questions? Yeah, Florian, go ahead.
Hi, thanks for the nice talk. I probably missed it, sorry. So I had a question, how can you distinguish single electron S2s, for example, from S1s? Do they have a different waveform or?
The S2 signals are delayed. As you can, let me go back to one of my previous slides. Do you see the slide?
Yes, thanks, yeah.
Yeah, so S1 induced photoelectrons create S1 prime signals, and the ionization electrons create the delayed S2 signals because of the longer electron drift times in the liquid. So they are clearly resolved, and you can clearly distinguish between photoelectrons created by S1 extracted from the photocathode and the ionization electrons, if that was your question.
Yeah, so I was wondering because what would happen if you miss, for example, this S1 prime, but yeah, we can also discuss later in the session, in the coffee break. Thanks.
Okay, thanks. There are no other questions, I think. So thanks again. Oh, there's someone.
I just want to ask, what's the possibility to build a larger, like a diameter one? What's the largest size you can build in terms of also, you want to keep the uniformity along the entire plane?
Sorry, could you repeat your question again? Are you asking if we plan to do tests with larger prototypes?
How difficult to build a larger size, like for Darwin or for G3, that will be 2 meters, 3 meters of diameter. Is that possible to build this?
That's a good question. And this is, I think, part of our future R&D on this project. So we would, of course, like to test this. This is a small prototype. We would like to test a larger prototype in future to see how stable it is.
Okay.
Yeah, that would be very interesting to see.
Yes, yes.
Okay, so I would suggest we go to the next one. If there are more questions, you can post them in the chat. So thanks again. So the next talk will be Louis. Are you there? Yes, I can see your slides.
Slides, full screen.
Yes, very good. So we can also hear you, so please go ahead.
Okay, so first, thanks to the organizer for this opportunity. So I will report on behalf of the PEN consortium about this particular development, which is the usage of PEN as cell between structural material in Legend. So this is the outline of my talk. So first, just a short introduction. I'm not going into details. So Legend is a neutrino-less double beta decay experiment. So I just want to remind what is the experimental signature that we are looking for. So if neutrinos are Majorana particles, what we expect is a peak at the end of the continuous spectrum of the normal double beta decay. So from the experimental point of view, what we want to have is the best possible energy resolution in order to disentangle the continuous from the neutrino-less double beta decay peak. And since we expect only a few events, so we want to have the lowest possible background. So what is the approach that Legend is using to looking for this neutrino-less double beta decay signature? So we use a germanium detector enriched in germanium 76. And the use of germanium detector provides the advantage that we can have the best possible energy resolution on the field. And in addition, the source and detector are the same instrument. In that way, we can have high detection efficiency. The germanium can have a very high radio purity, which means that we don't have intrinsic backgrounds, which is very good. And complementary to that, the detectors are operated in liquid argon, which is used to cool down the germanium detector, and also as active shielding. So the signature that we're looking for is a kind of a point-like signal in the germanium detectors. And if we have some, for example, radiation coming from outside, and we have a scattering in the germanium detector, we can disentangle this with the PSD capabilities of the germanium detectors. And if we have same events, but with the interaction with the liquid argon, so we can use the light from the liquid argon to remove this type of backgrounds. So there is a very good complementarity between the germanium detectors and the liquid argon. So, and this approach has been proven very efficient, as proven previously by the Gerda experiment. And ideally, we will want to have only the germanium detectors and the liquid argon and nothing else. However, we need all the infrastructure to deploy the experiments or deploy the germanium detectors. So here you can see how it looks like a single detector and the support structures. So we need to minimize the materials that we put around the detector, because 100% radio purity is not possible, and all these components that we use to mount the germanium detector will produce some backgrounds. For example, some gammas can scatter on this support structural and then completely absorbing the germanium, and that can mimic a signal. We want to avoid that. And also some radio impurities. So for example, a gamma can leave a bit of energy in the structural materials and then completely absorb in the germanium detector, and that also can mimic a signature. And if we look at the current status, so here in this kind of table, we have the status for the current phase of Legend 200. So here we have the different backgrounds, and I just want to call your attention for this component, which is produced by the NIR components, which are all the materials that we use to mount the germanium detectors. So this is a status what we expect for Legend 200 currently being deployed. And this is what we need to achieve if we want to reach the goals for the next phase, Legend 1 ton. So the question is, can we do better than we have done so far? So the material has been already optimized to minimize the mass. So there is a little margin there. So then the new approach that we're trying to push is replace these structural materials which are inactive for some active material. And we think that we can do that by using PEN, which is polyethylene naphthalate. And in that way, we will have this similar type of backgrounds. This will scintillate, and this will produce light that can be used to identify this type of backgrounds. So this is the approach that we're trying to develop. So why PEN? So PEN is commercially available, so we can buy it, and it's already with a good radio purity. Has a yield strength higher than copper at cryogenic temperature, which is good to operate in cryogenic liquids. And in addition was first evidence that it scintillates, and in addition it has wavelength shifting capability. So we have both properties in the same material, scintillation and wavelength shifting properties. So all these make a PEN ideal candidate to use as a structural material with cell between capabilities in cryogenic liquids. So we need to produce thick shapes. So to do that, we just need to take into account that it's a semi-crystalline polymer, and this can lead to non-transparent shapes, as you can see here. But nevertheless, with the work that has been done in the past, it has been optimized the settings to produce very transparent shapes using the injection compression molding, and almost any arbitrary shapes can be produced using this technique. And so a lot of shapes, arbitrary shapes has been produced. And also the ORNL group of the consortium has developed also a synthesis of PEN, which can help to improve the radio purity. So what is the process going from the raw material to achieving a high purity scintillating material? So the material can be ordered in the form of pellets, as you can see here. Then we have developed a cleaning process So this is the radio purity that the raw material that was measured. Then we develop a cleaning process and injection molding under clean room conditions. And this is the radio purity that was achieved after all the process. You can see that we have improved from the raw material to this kind of disc of plates. And using these plates, we develop also a machining under clean room conditions. And in that way, we have measured these limits. And so these limits are basically because the mass that we use for the measurement is much smaller. But nevertheless, confirm that basically no noticeable radio impurities were introduced during the process, which is good because we have produced these active support structures with a high radio purity. Then, so since this material is being used by the first time in Legend 200 as active structural material, so most of the optical properties are not well known. So to try to measure this property, we have mounted several setups, and also we have developed in parallel jam force simulation, because for some of these properties we need to combine data with Monte Carlo. So we have mounted setups where we can place, for example, in this setup, pen samples and samples from other scintillators, and in that way we can have direct comparisons and then extract measurements of the light output. So we can use longer samples and excite the samples at different points, and in that way we can measure the attenuation and the bulk absorption and also the emission spectrum using a spectrometer, for example. So we have already some first estimations for using this setup. So we have measured the decay time or excitation time of pen. So you have here the emission spectrum. We have measured extracting the sample at different distance from the collection point, and you can see basically that it shifts to the right. And basically, this is because the bulk absorption around 400 nanometers is important in the case of pen. So this also limits a bit the size of the sample that we can produce with pen. And we have measured also the attenuation. We have developed the simulation, and at the moment we have already a very good agreement, so we can reproduce the attenuation of the samples that we are using. And we have also some estimation of the bulk absorption, so as the bulk absorption in millimeter as function of the wavelength. So you can see that 400 nanometers is very important, but above 450 nanometers is a bit better. And also there are work ongoing to try to study all these properties in liquid argon temperature and in near to final operational conditions. So the radio purity that we have now is already very good. Nevertheless, for the next phase for Legend 1000, we might need better radio purity, and to do that, the idea is replace the first stage of the process. So now we have used commercial material. So then the idea is that we can do the synthesis ourselves, and then repeating the process under controlled condition, we might be able to improve the radio purity, which is good for the next phase for Legend 1000. And also there are work in parallel that is being developed, for example, high purity 3D printing of pen parts, scintillating and transparent parts. There are already good progress on this matter. And also we are trying to explore other possibilities for Legend 1000. So there are other backgrounds that we want to see if we can remove by using pen. So we have a background which is produced by argon 42, which decay in potassium 42, and then these ions are drifted to the surface of the detectors that produce background. So we are exploring the possibility of developing encapsulation of the germanium detectors. In that way, we can protect the germanium detectors from this type of background, surface background, basically. We have already produced some capsule that we are trying to use right now to make some tests and validate this approach. And also we are exploring the possibility of using mini shrouds or made of pen, kind of coating around the detectors that also can help to protect the German detector from this type of backgrounds. And we are also developing the Monte Carlo to study the efficiency and viability of every one of these options. So with that, just let me summarize what we have done so far. So I hope I have convinced you that PEN is an attractive solution to use as an active structural material. We have performed a successful production of low background PEN holders for Legend 200, starting from raw material. The design of this holder was optimized for this phase. And we have developed also a protocol for production under clean room conditions. A publication will be coming soon. And the optical characterization is ongoing. From this optical characterization, I'm making a direct comparison with other scintillators. We know that the LIDINE is at least 3,500 photons per MeV. We're developing the Monte Carlo to try to extract the absolute value of the LIDINE. And also we have some preliminary estimation of the bulk absorption. So for example, we know that it's at least 50 millimeters, around 450 nanometers, which should be enough for small components that we are planning to use in the LIDINE experiment. And we are developing also the simulation to all the setups in order to obtain absolute values and decrease uncertainties. And the next step is just to complete the optical characterization and the wavelength shifting capabilities, and continue with much more R&D for Legend 1000 and study the possibility of application of this type of components in other experiments. So that's all what I wanted to show. Thanks for your attention. I don't know if there are questions.
Thanks a lot for this really interesting talk. So we have time for a question. So on your slide 14, maybe I can ask the question. Looks interesting, this encapsulation. So so I don't have no feeling for the size. So how large is this? For example, this one on the photo on the right.
So yeah, so this capsule, so the size of the detector that we will use in Legend 200 and Legend 1000 are 2 kilograms, more or less, mass of detector. So yeah, the capsules are, the size of the capsule is that we need to use is to encapsulate a 2 kilogram germanium detectors. So that gives more or less an idea of the size.
Yeah, it was hard to estimate if it's really small, or I mean, I guess you have some limitation how to scale this, right? To how large you can really use this, but
yeah, so yeah, the limitation basically are given by the molding process, but we still have margin to make bigger capsules. So the diameter of this, just to give an idea, is about 7 centimeters.
Okay. Yeah, thanks. Oh, there's one more question. David, I think we have time for that question.
Yeah, thanks. Interesting talk. I'm wondering, so is the plan to instrument these encapsulation devices and then use it as like a veto?
Yeah, that's basically the idea. So at the end, the goal is develop a kind of a complete encapsulation and structure made of PEN, scintillating PEN. And yeah, then there are several possibilities. So if you want to optimize the light collection, probably you want to place a photosensor close to this capsule. But since the transparency is quite good and the attenuation in liquid argon is also good, you can imagine that you can place photosensor far away from the detector, which is also good to decrease backgrounds induced by the photosensors and the electronics.
Okay, nice. Thanks.
Okay, thanks a lot for this talk again. And I would suggest we go to the next speaker. Cenk, are you there?
Yes, I'm here.
Very good.
I am just about to share my screen. Okay, can you see it?
Yes, we can see it. So please go ahead.
And you can hear me clearly, I guess. Okay.
Yes.
Right. Okay. By the way, yeah, just in case. Sorry. Okay. Okay. Hello everyone. First of all, my name is Cenk Türkoğlu, and today I'm going to talk to you about our work on polyethylene naphthalate wavelength shifter development and comparison with TPB using 2PAG. This presentation I'm going to give today is the direct result of the paper that we put on archive some time ago. And if you want to check it out, I left the archive number here. So I know that like many people already talked about PEN and TPB or wavelength shifters, but just in case, so I just want to give you some short summary. So we know that particle experiments, which uses liquid argon as a detector medium, due to its high scintillation yield and its ability to drift ionization charge over long distances. And the thing is, the scintillation light emitted from liquid argon is in the UV range, but the photodetectors are insensitive to vacuum ultraviolet light, so wavelength shifters are used to convert ultraviolet light into optical light. Here you get a simple representation of this. And the TPB, which is the most common wavelength shifter, stands for, it's coated on surfaces using vacuum evaporations, and requirement for productions of these coatings are high vacuum conditions, and because of this, it is difficult to scale up to hundreds of square meters of surface area. So, but there's a problem with that because future particle physics experiments are trying to scale up in size. And the condition I told you about regarding the scaling up problem makes it harder to employ TPB as a wavelength shifter. So polyethylene naphthalate, which is produced as a polymeric film, was recently proposed as an alternative to TPB. And PN has a few advantages compared to TPB. It's available as a film and it is scalable, and it is relatively inexpensive compared to TPB. But the earlier estimates on the wavelength shifting efficiency of PEN relative to TPB had some problems due to the large uncertainties caused by the temperature and excitation wavelength dependence of fluorescence process, and the variation between different samples and grades, as well as geometrical effects. So in our work, what we do is to make a direct comparison of TPB and PEN based on light yield in two identical chambers filled with liquid argon. And the setup in this work actually is representative of the geometries used in the liquid argon detectors, such as DarkSide 20K, which is the experiment I'm working on, but the veto part of it, where photodetectors cover only a small fraction of the surface, which is a few percent basically, and the rest is lined with the wavelength shifting reflectors. So let me give you some information about our setup. A dedicated detector setup was produced for this test and named 2PAG, which stands for two parallel argon chambers. And you can see a photo of it on the right. You can see that it is made out of cylindrical aluminum chambers, and in both end caps there are SiPMs, which are used to detect the photons, and there's also spacer rings at the edges. Approximately 1% of the inner surface is covered with SiPMs, and the rest of the inner surface is covered with enhanced specular reflector, ESR, with a high level of reflectivity of visible light, which is around 98%. So the chambers are different by the wavelength shifter that is used inside. So one of them has the ESR coated with 3 micrometer layer of vacuum evaporated TPB, whereas the other chamber has 25 micrometer PN film, which is a Tionex Q51 grade, attached in front of the ESR with up to 1 millimeter of liquid argon gap between both films, maintained by spacer rings at the end caps. So the data taking took place at LNGS, and a small surface coverage fraction of the SiPMs, which is what we call F here, forces wavelength shifted photons to be reflected on average 1/f times before they reach a SiPM. And this leads to the overall light yield to be very sensitive, not just to the wavelength shifting efficiency, but also to the effective reflectivity of ESR and wavelength shifter. So also, a dual chamber setup gave us the opportunity to make a one-to-one comparison by having the same liquid argon bed, which means the same purity liquid argon and the same source. And all of this actually reduced the systematic effects. And to extract the light yield of the 2-pack detectors, we used americium 241 gamma ray source which emits 59.5 keV gammas. So this americium source was placed on the outer surface of the devar, which corresponds to the center of the detector system, basically. And you can see the rods holding the 2-pack setup on the right photo, and on the left you can see the cryostat, basically. So how did we do the analysis? So basically, first we took the background data without using any kind of sources, which you can see on the top 2 plots on the right. In the blue dashed line, the top one is for PN and the bottom one is for TPB. And then the peaks in the data retrieved with the presence of the source are fitted with Gaussians, and you can see the data retrieved with the source in the red dashed lines here on the top 2 plots again. And then the number of photoelectrons below the peaks are counted and summed up for both SiPMs in each chamber. And then the light yield is calculated by dividing the sum of the detected photoelectrons to the energy deposited in the medium. And after pulsing and crosstalk, these are corrected based on calibration. And the results for the second run, which you can see in the bottom photo on the right, show a 15% decrease in light yield, where the top ones are for TPB and the bottom ones are for PN, where red is the run 1 and the blue is the run 2. So there's like a decrease in the second run, basically, but this can be explained by different purity of the argon in the system. And in the end, when we calculated the light yield of PN and TPB and divide them both, we got a ratio of 39.4%, with 0.4% of statistical and 1.9% systematical uncertainties. And the systematical uncertainty here includes contributions from residual top-bottom asymmetry and the difference between the runs. And this 15% decrease in the light yield in run 2 is actually included in it, and this ratio is affected by this reduced light yield of the second run by less than 2%. So also we did some simulations on this, basically, and what we did was do G-force simulations in order to disentangle the effects of wavelength shifting efficiency and reflectivities on the final light yield. So we in this simulation, we included geometry and the optical properties of all materials. And this Monte Carlo result actually was validated against a simplified analytical model. And the reflectivity spectra used in the ESR, used in the simulation for ESR, and TPB quoted ESR, PN air coupled to ESR, and SciPMs have been measured using a spectrometer with an integrating sphere accessory, and the results of this can be seen on the right. And other parameters used include the emission spectra of PN and TPB at 87 Kelvin, and the absorption of vacuum ultraviolet light in liquid argon and of visible light in liquid argon and in TPB was considered negligible. So wavelength shifting efficiency of TPB was set to 100% because the aim of this is not, the experiment was not to get an absolute wavelength shifting efficiency of PN, but one that is relative to that of TPB. And the systematics revolve around the reflectivities of different components of the setup, which include inner walls, dead spots in holes, and SciPMs. And the dominant systematics come from, as you can see on the table on the right, uncertainty on the absolute calibration of the reflectivity measurements and the losses due to the fraction of 2-pack surface not covered with the ESR film. So the Monte Carlo simulation was used to evaluate the relative wavelength shifting efficiency of PN with respect to that of TPB from the observed light yield, and the resulting value for this wavelength shifting efficiency of PN relative to TPB for the specific grade, which is a 25 micrometer thick T1X Q51 foil, turned out to be 47.2% with an uncertainty of 5.7%, which is dominated by the systematical error. And this is a higher result compared to the previously projected results for other PN grades, such as 125 micron thick T1X Q53 has this same value, same ratio, sorry, with 34%, and 125 micrometer thick T1X Q83 has the same ratio, for the same ratio has 38%, basically. So, in conclusion, like scaling up of experiments employing wavelength shifters make TPB a less viable option. And another wavelength shifting shifter PN was introduced as an alternative to TPB because it is produced as thin films. And the 2-pack experiment aims to compare the wavelength shifting efficiency of these two materials in same physical conditions. And the one that we used here, which is the T1X Q51 PN film with 25 micrometer thickness, had a relative wavelength shifting efficiency to TPB as 47.2%. And for future, we know that wavelength shifting efficiency of commercial PN varies among different grades, and there are multiple factors affecting this parameter, which are thickness, additives, and composition. We continue the R&D on optimizing the custom synthesized PN films for higher wavelength shifting efficiency. And for this, we need a facility for absolute wavelength shifting yield characterization at 128 nanometer at 87 Kelvin. And we are also looking for an industrial partner to help us with this, basically. Thank you very much for listening to me. If you have any questions or comments, I will try to answer them. Thank you.
Thanks a lot, Cenk. this nice talk. If anyone has a question, we're a bit tight in time, but I think for a short question, we would have time. I was just wondering, on slide 9, you showed the different reflectivity curves, and just out of curiosity, how is it coming for the silicon PM that there is this fluctuation happening? Maybe I missed it.
No, it is kind of the way the SciPM reflectivity was measured. Unfortunately, it gave a continuous spectra, but the problem is it is caused by this anti-reflective coating on it, basically.
Okay, I see. So that's what you mentioned. Okay, thanks. So then let's thank you again, and let's go to the next talk, Gabriela.
Yes.
Thank you.
Can you hear me?
Yes.
I'm waiting. Yes, great. So now I can share. Can you see my slides changing?
Yes, perfectly.
Great. So yes, so my name is Gabriela from the University of Zurich, and I'm going to talk about the R&D and characterization of wavelength shifting reflectors for legend and future liquid argon-based detectors. So we start with the first motivation for this work, which is the wavelength shifting reflectors of Legend 200. So as described by Stefan on Wednesday and Luis previously today, the determinant detectors in Legend are immersed in liquid argon, which is instrumented with wavelength shifting fibers coupled to silicon photomultipliers to act as an anti-coincidence veto. In this system, a shroud of wavelength shifting reflectors surrounds the green fibers in order to increase the light collection efficiency of the system. And the way it does that is by both shifting the UV light and reflecting the shifted light towards the fibers, so that the fibers can absorb this light, as you see here in this spectrum. In Legend 200, 13 square meters of wavelength shifting reflectors had to be prepared to surround roughly 6 tons of liquid argon. And as mentioned by the previous speakers, in future experiments, much larger volumes of liquid argon will or might have to be instrumented with wavelength shifting reflectors, such as Legend 1000, Darkside 20K, and possibly Argo. And yes, you heard in the last talks about PN being easily scalable wavelength shifter. So that's a second motivation for my talk, to investigate this material as a scalable WSR for large detectors. And when talking about wavelength shifting reflector materials, there are two things that are very important. First, their UV shifting efficiency towards the visible, and then their reflectivity of visible light, or absorption of visible light. So in this work, we measured these parameters, and I start with the vis reflectivity and absorption. So we used a spectrophotometer with a calibrated integrating sphere to measure the reflectivity and absorption of several materials in response to light from 360 to 600 nanometers. Here we focus on theta tags, which is a thin PTFE-based reflector, and then on films of evaporated TPB or sanded PN coupled to it. A few reasons for focusing on theta tags is that it has been used by Gerda and RDN before, and it has been proved to be radio pure, low outgassing, and highly reflective, as you see here in our measurements. The absolute reflectance of theta tags is over 94.5% in the blue region. After theta tags, we then measured the TPB and PN films coupled to theta tags, and what we observed is that the measured signal decreased because a layer of evaporated TPB or sanded PM absorbs some part of the light. decreasing the observed signal, as you see here in the blue and green curves compared to the blue and green compared to the gray curves. From this, and with the help of a second spectrophotometer, we quantified the absorption lengths of the investigated TPP and PN films. And what we got from these measurements is that even the case PN and TPP had the same quantum efficiency, the light yield from the PM with theta tags would be lower because more light is lost in the PN film. So for Legend 200, 600 nanometers of TPP were vacuum evaporated on the surface of the theta tags and side Legend's cryostat. The thickness was chosen so that it performed best in response to UV light while not absorbing much of visible light, as you see here. An evaporator was designed to coat the TPP inside the 7-meter tall cryostat. And here shown a schematic of what the evaporation process, the reflectors before evaporation and during evaporation under UV light. A few extra samples were evaporated together in the same process, serving as witness samples of the evaporation. These samples showed optimal fluorescence in response to UV light and were used for further characterization in liquid argon. And this brings me to the second focus of this work, which was to characterize the Legend witness sample and estimate the quantum efficiency of TPP and PN in liquid argon. But before doing this, we can characterize the samples with microscopes to make sure that they look good so that we can indeed extract these efficiency parameters from the samples. Here showed the scanning electron microscopy of bare theta tags on the top and of the in situ evaporated TPP of Legend on the bottom. As you can see, the evaporated films, the evaporated TPP fills well the pores of theta tags, and this was observed in several scales and to scan even large areas of the samples we then use fluorescence microscopy. And with this, we checked the uniformity of TPP coating in samples of up to square centimeter size. On the right, you see a single scan from the tile scan of the left. And for comparison, you see a scan of a theta tag sample deep coated with TPP. This sample shows crystallization in large areas lacking on a good TPP coverage, which is clearly not the case of our Legend sample. We also exposed a part of a sample to ambient light for 2 weeks and observed no change in the light yield from the exposed sample in comparison to the non-exposed one. Now for PM, we just imaged the sample to see the effect of sanding its surface. As you see here, sanding the sample did not produce a completely rough or diffusive surface, but the interesting thing is that more light is observed from the scratches, indicating that photons within the PM undergo total internal reflection and can more easily exit through a diffusive surface. Then we finally measured the theta tags coupled to PM and TPP on theta tags sample from Legend in a liquid argon setup. Here's a few samples wrapped around the sample holder, which then coupled to a PMT and goes inside the cryostat where liquid argon is condensed by the copper coils until the cell is completely filled with liquid argon. In this sample cell, we avoid uncertainties from the reflectivity of its structure by covering them with a low outgassing absorber, which has a very low reflectivity from the extreme UV to the far infrared. Then we have mostly the sample as the main surface in the cell, and an americium 241 source induced liquid argon scintillation photons inside it. These photons can be directly detected by the PMT on the top, since the PMT is sensitive to the UV light. The size of this PMT is 3 inches, so it has a good coverage of the light yield, and the fact that it is UV sensitive, along with the well-localized source of photons, makes the setup very interesting, because by using an absorber as a reference sample, we can then characterize the specific VOV light yield of the setup, and then compare this value to the light detected when measuring a WSR sample. So for instance, we measured around 550 photoelectrons for the absorber, and this number increases to 1250 photoelectrons for TPB on TTTEX, because we additionally measured the light shifted and reflected by the TPB WSR sample. To ensure this increase in light detected is indeed due to shifted light, we redid all the measurements in a visible only mode. In these measurements, an acrylic window blocked the UV light from reaching the PMT, and only visible light was measured. From the vis only measurement, we get around 700 photoelectrons. And when we sum this value to the value measured with the VUV only mode with the absorber, we do get the 1250 value we got before for the VUV plus visible mode. So now that we see this values match and that the measurements not suffer from large systematic uncertainties, we run a Gen 4 simulation so that the simulated number of photoelectrons match the one detected in the measurements. We do this first for the absorber measurement in order to find the effective light yield in the setup. Then we input this value in the simulation of the wavelength shifting reflective samples and attribute the enhancement of detected light to shifting and reflecting of photons by the WSR sample. We do this for several quantum efficiency values, with higher quantum efficiency values yielding higher P values. The simulated quantum efficiency that matches the data, of course, depends on the geometry of the sample, of the setup, and optical parameters of the sample input in the simulation. Most of the optical parameters for the simulation are listed in the backup slides, but here I list some of the most relevant ones. Most of them we measured with the spectrophotometers I showed before, or even by characterizing the samples in liquid argon previously. And as you see here, a few of these values were measured in air, such as the visible reflectivity of TTTEX, or have large uncertainties, such as the UV absorption of TPB. So we run a simulation for all these different values, accounting for all these uncertainties. This means that we obtain, so to say, expected value for the quantum efficiency of these films if we input the mean values of these parameters in the simulation. But if we input all their uncertainties, we get rather a lower limit on their quantum efficiency. These are yet preliminary results, as we're still working on the manuscript of this work. But for TPB, these were the first measurements of its quantum efficiency in liquid argon in a well-characterized setup. The value for TPB agrees with the room temperature value previously measured by this group, corrected for the increase in efficiency expected at liquid argon temperature. For PM, these were the first measurements of its efficiency independent of TPB. And if we compare the light yield to TPB, the values we measured were actually a bit higher than those previously published and also in the previous talk. But a few differences are we had a very large coverage with the PMT, and the film was attached to TTTEX, not to ESR. And the PN sample was sent. To conclude, I show here a few pictures of the evaporation of the 13 square meters of TTTEX with TPB done inside the legend Kronstadt, and with the measurements of the samples that we did with microscopes, spectrophotometers, and in liquid argon setup, we were able to estimate the quantum efficiency of TPB and PM in liquid argon for the first time. So these results can now be put in the simulations of the liquid argon veto of Legend. So that's all. Thank you, and I'm happy to take questions.
Thanks a lot, Gabriela. Was a bit worried with the number of slides, but you went really nicely on time, so we have time for a question. No one. So on your on the slide before, you showed now the values you got for the difference. So you have a higher quantum efficiency than with a TPB with pen. So you also had this mixed state. So I got a bit confused. Or is that now? So you had the TTX plus pen and TPB. So is that now purely by themselves, or is that now in one of the states together? Sorry, I maybe missed that.
Quantum efficiency is really from the materials. So here we really try to decouple like the light yield we measured of TPB with the reflector and get really to the intrinsic quantum efficiency of the material. So this is not really related to only the light yield we got, but really kind of taking all the optics of the samples and of the reflector into account. And the same is true for PN. Yeah.
Okay, thanks. David, short.
Yeah, hi, Gabriela, nice talk. I had a question, so maybe I missed this, but these values for liquid argon temperature, or?
Yes, exactly, because all the measurements were done in liquid argon. So yes, the values we got are for liquid argon temperature and liquid argon scintillation.
That's great, thanks.
Okay, thanks again. Really nice. So now we go to the last talk of this session. Michael?
Oh, hi, can you hear me?
Yes, very well.
Okay, share slides. So can you see the slides?
Yeah, full screen mode.
Can you see them changing?
Also that.
Good for me. So the last talk will be about, oh, nice. Okay. So the last talk will be about a photo sensor called CMOS-based sputter rays. We are working on that, and we think that it could be a nice solution or a nice detector for upcoming revenge search experiments. So what are they? They are CMOS-based sputter rays are technology where you have spuds and the custom-made readout electronics manufactured side by side. So you can see it in the example here below. We have a photo of our chip with a zoomed-in level or zoomed-in view to the pixel level, where you have the spuds in green and the readout in red. So you have a fully functional detector on a single chip. There is no additional ASIC needed to read them out or any other discrete electronics like for normal SIPMs. And the output signals are also purely digital. That's why they are called also digital SIPMs. Of course, for a revenge search experiment, we build our own prototype or a new, mostly driven by the Darwin experiment, where we are part of. And we optimize it in that way that we have a nice high fill factor and a low power dissipation. To get a nice high fill factor, we have implemented a so-called macropixel test structure, which includes 10 spuds, and they are read out by only one readout circuit, and only one readout or one common hit signal is then sent to the periphery. And both spuds have different shapes and aspect ratio to check how the dark count rate scales with it. So that's why it's a test structure. And noisy spuds can be of course turned off to reduce the overall noise and select one of the spuds for a measurement. On the right side, you see the whole detector. We have 361 macropixel. Our overall readout is a low power CMOS only one. It delivers a binary X and Y address of a pixel which was hit. Multiple hits are not processable, but for low rate, it doesn't matter. Here are two microphotographs of our chip, where you can see left the matrix and right the macropixel structure. Nice thing was that within the submission of this prototype, our manufacturer granted us technology variation, which tackles two main problems. First was to reduce the dark count rate at lower temperatures, which is dominated by band-to-band tunneling. Until now, we have received 3 wafer types, which I have successfully tested now, and will show you the best results in a minute. The second thing is to enhance the QE at VUV light. This is important for xenon. Then processing is a little bit delayed due to the coronavirus, but we should receive them soon and then start hopefully to measure the QE for those. Just to give you a hint for the QE, for visible light, our manufacturers already measured it, and it is about 45%, around 400 nanometers. And for VUV light, where we'll implement the so-called POB process, where you have a responsivity curve of a photodiode, in this case below, where are drawn in the QE, or the line corresponding to 40% QE. So it should be a quite nice process. How it turns out for our spots, we don't know, but this is a quite promising paper or result they already gained. Of course, we measured the dark cone rate at lower temperatures, and for this we have a nice cryo setup. It's a liquid vacuum nitrogen cryostat. We have the reservoir here on top. You can pour in liquid nitrogen from the top and attach to it with weak thermal contacts. You have an experimental platform where the chip sits. You have an LED to illuminate the chips at all temperatures. It's a low temperature LED. And we have a PT100 thermometer and a heater to set up the temperature between 100 Kelvin and 300 Kelvin. Exactly. Here are a photo of, or on the right side, you can see the whole experimental setup with the working cryostat and the rack with all the measurements set up. And on the left side, you can see it turned upside down and open with like liquid nitrogen reservoir, and on top you see the chip PCBs. First thing we asked ourselves was, how does the dark cone rate, or with a macropixel we could ask ourselves, how does the macropixel scale, or the spot size actually scales with the dark cone rate, or the other way around, the dark cone rate with the area. And you can see it here at two temperatures, at room temperature and 160 Kelvin, which corresponds to liquid xenon. And you see a slight drift here at room temperatures, but it's only about 20%. Others here have deviations of about one order of magnitude. Of course, the dark cone rate is here normalized to the active area, and the hotspots are excluded from this analysis. And on the right side, you can see at low temperatures the points are scattering wildly, so there is really hard evidence for any effects on the area. This means we can go large for our spots in the macropixel and get a nice high fill factor, like already mentioned. Here's a plot for the overall dark cone rate at low for various temperatures, and you can see it drops quite steep for higher temperatures, which is due to thermal generation or reduction of thermal generation, which drops exponentially with temperature. And then you run into a kind of plateau, which corresponds then to the band-to-band tunneling noise. And you can see that we reach a value of about 0.01 Hertz per square millimeter, which is actually one order of magnitude better than I or reported in the abstract, because I did some new measurements, which turned out to be the best at all. And compared to our previous measurement, which I also showed at last LIDINE conference, where we reached 7 Hertz per square millimeter at liquid nitrogen temperatures and 20 Hertz per square millimeter at liquid xenon, we are now 3 orders of magnitude better, which is quite nice. Power consumption is also very promising. We have a data-driven readout architecture, which means only if there is a hit, power is consumed and the readout is working. So it should scale linear with the power consumption should scale linear with the rate, and it does. We have a slope of 15 microwatts per kilohertz detected photons. And the DC power consumption is also only about 1.7 milliwatt, which is independent of matrix size. It's just the slow control and the ducts which are drawing some current, not the pixels. And those results gave us made us think about a large-scale detector concept. For future upcoming rare event search experiments, where we wanted to stick with an asynchronous readout, which because it has a low power dissipation, but this time the macropixels shouldn't send the hits out directly to the periphery, because we wanted to be capable of processing multiple hits this time. We now start to scan the rows and columns for the hits. Therefore, you have a scan unit here at each row, where you activate the scan in, which falls through if there's no hit in a row, but stops and activates the row for readout, for the column scan actually, and presents the address here to the data from the row to the data processor. And also on the column, it repeats again. You select the row which hasn't hit, collect the address, and then with a timestamp, which will be collected row-wise in this case with a resolution of 1 nanosecond, and then shift all out to the data processor. Nice thing is we have already implemented such a, or I have already implemented such a row scan unit, and it works quite nice. So it's straightforward to implement for us. The overall data protocol when look like this, we think of a 1-bit serial output or of a hit data, which is really simple, and it should result in a large shift register. So you daisy chain the chips together to a large shift register, several chips, and then clock the hit data out. Hit data will be about 74-bit wide, which includes timestamp, address, and the ID of a chip, obviously, to distinguish them. And the command processor here on the bottom will then flag if a package starts, and if the serial in will also flag if the package is full or empty, and if it's empty, your readout can inject data to a long shift register and clock out the data over several chips then. The overall pin consumption will be only about 7 pins, so you can really read out a large detector plane with only 7 pins, which makes electrical feed through really nice. And our model concept will then look like this. You have 4x4 or 6x6 chips, which we did not, which will be optimal size, I think. And the PCB or the support structure won't need any electrical contactation at all. So there's any material you can think of, you can use to glue the chips on. And the chips will then connect it to each other with on-chip bonds. So you bond from one chip, wire bonding from one chip to another, and read out the whole plane. So in summary, digital SRPMs are, of course, a promising candidate for rare event search or for upcoming rare event search experiments. We have nicely reduced, or our manufacturer was able to nicely reduce the band-to-band tunneling noise about 3 orders of magnitude, which then corresponds to a dark count rate of 0.01 Hertz per square millimeter below 100 Kelvin, and 0.02 Hertz per square millimeter at liquid xenon, which is actually comparable to all known standard or commercial SRPM technologies which you can buy. So FBK or Hamamatsu reach quite the same noise values. And our proposed readout architecture offers around 80% fill factor, which we have actually measured, but it is possible. We have a low power dissipation, which should scale only with a hit rate. We have simple mechanics. The material budget is really low, so you can have any material or support structure you want. We need only a few cables, in principle less than 10 for a full detector. This is not quite feasible because you have both modules and do not have a dead chip within such a module. And we have a high spatial resolution, which will be in the order of 300 or 300 micrometers, and temporal resolution of about 1 nanosecond. The last question, which we have to answer, is now how is our QE at VUV light, and at 400 or visible light, we already knew this is about 45%. So, thank you very much.
Thanks a lot, Michael. It was a really interesting talk, and we already have 2 questions. So Fabrice was first.
Yeah, okay. Actually, I have many questions, so thanks. It was very interesting, but I will just ask one, and I will contact you for the rest. I'm on slide 12, I think. That's where you have your architecture. The
yes.
So I guess I have a dual question. Why do you need to address each SPAD, and can you do better than 1 nanosecond resolution? So because for me, I would prefer not having the address of each SPAD, but having better timing resolution. Is this possible?
In principle, it would be okay to do this. This is not yet fully decided. We can, at least you can have any architecture you want. And of course, we have a small circuit which actually fits in every pixel, which yields around 100 picoseconds timing resolution. So this is actually not the limit. But if we are aiming to do the timestamp with a normal counter, and there you need a gigahertz to get this resolution. But we can go below. It's easy for us.
Thank you.
Okay, so let's go to Sven.
Yes, I have a question about the DACAM rate. You report these hotspot exclude. So how many percentage of them are hotspot? And
that's a good question. That's actually scales with temperature and with the size of a dark hole or with the size of a spot. At room temperature, this largest spot here, which is shown here, is actually 80% of them are really bad. If you go below here, you reach 5% or even lower. But if you go to low temperatures like 116 or even 100 Kelvin, the number shrinks. So you end up with around 5% at 100K. So you mostly can use all of them and do not leave any active area with those.
Because of the imperfect fabrication process?
No, I think hotspots is a problem also for normal SLPMs. They just have to pick really careful their designs, and we can exclude them by a hardware switch, which makes also the yield quite better compared to commercial technologies.